I want to give you another strategy for solving these conservation of momentum in 2D questions. So I picked number 4 from the first homework page. I think that's right. I think it's from the first one. I'm not going to read this to you, but you can read it yourself if you'd like. This is one more strategy you can use. There's actually a whole bunch of ways that you can solve these types of questions. So here's what I'm going to do. I'm going to go before and after. So what we're trying to do, that says atter. Ater? There's an F. That's much better. Let's just try this again. Okay. After. There. So another strategy that you can use is to account for what's all the x momentum at the beginning before collision. That should be equal to the x momentum at the end after collision. What's all the y momentum at the beginning? That should be equal to the y momentum at the end. So I'm just going to look at the before. And so in the before section, we have one ball moving 2 meters per second north. So that's going to be a y momentum. The other ball is not moving at all. Okay, so we've really just got y momentum. So at the beginning, the y momentum that's there is just, well, let's just go mass of ball 1. No, let's go mass of ball A times velocity of ball A. Okay, and that's 0.5 times 2. 0.5 kilograms times 2 meters per second, which is 1 kilogram meter per second. And that's in the north direction. So how about let's go like this. North is going to be positive, south is going to be negative, and then things are happening to the west. So then we need a second version of that. So since things are happening to the west, let's call west positive and east negative. Okay. So far, we're only using the north-south one. So this is positive 1 kilogram meter per second north. The x momentum at the beginning, 0. That's both balls. So ball number 1 doesn't have any x momentum. Ball number 2 doesn't have any x momentum. Okay, and so we know that after collision, the two x momentums should add up to 0, and we know that the two y momentums should add up to 1 kilogram meter per second north. Okay, so now if we look at the second part, the after, it tells us that the first ball is deflected at an angle of 30 degrees west of north with a speed of 1.5 meters per second. Okay, so looks like this. West of north. I can do this. There you go. Here's north. This is 30 degrees. Okay, so we have two components to that momentum. We have our y component, which is going to be northward. There's our y momentum. And we have our x momentum, which is going to be this way. Okay, so we need to calculate both of those components. When we're doing that, let's go black again. When we're doing that, we're going to use cosine for the y component and sine for the x component. Okay, so after, let's look at ball number 1. Or ball A, I called it. Ball A. Ball A has a y momentum, mass A, velocity A, y is equal to 0.5 kilograms times 1.5 meters per second times the cosine of 30 degrees. This equals 0.65. 0.65 kilogram meters per second squared. Not going to be able to read this. Not per second squared, just per second. Kilogram meters per second. This is the momentum of ball A in the north direction. Okay. The momentum of ball A in the west direction would be, I'm going to start it a little bit farther over here so I can actually fit it. Mass of A times the velocity of A in the x direction is 0.5 kilograms times 1.5 meters per second times the sine of 30 degrees. And that is equal to 0.375 kilogram meters per second. And that's to the west. Okay, so now is when we're looking at what does that mean about the other ball. Okay, so we know that the total y momentum at the end should be 1 kilogram meter per second. The y momentum of ball A is 0.65, and so that means that the y momentum that's left over for ball B would be 0.35 north, right? Because ball A's north momentum and ball B's north momentum, they should add up to 1. Okay, so we know that the momentum of ball B in the y direction has to be 1 kilogram meter per second minus 0.65 kilogram meters per second. Okay, so they've got to add up to 1. So what's left over for B is 0.35 kilogram meters per second, and that's in the north direction. Okay, so this piece is important. We're going to use that. And then as far as the x momentum goes, now I'm going to start it way over here. The momentum of ball B in the x direction, the x momentum in total has to be 0. Okay, but since ball A developed some x momentum when it collided with ball B, that x momentum that ball A has to be canceled out by the momentum of ball B. So the momentum of ball B must be 0.375 kilogram meters per second, but instead of west, it's going to be east. Okay, and so what we've got then is a triangle situation where we've got the north momentum like this. So we have the north momentum of ball B, which is 0.35. And we have the east momentum of ball B, which is 0.375. And so the total momentum of ball B is going to be to the northeast, like this. Okay, and that should hopefully make sense, because if ball A is doing this, so it's traveling north, it hits ball B and glances off this way, you would expect ball B to glance off the other way, right? And so that's what we find it does. It has a north momentum and an east momentum. And when you do a squared plus b squared equals c squared to figure that out, you should get 0.513 kilogram meters per second. Okay, you should also figure out what the angle is, and so that would be opposite over adjacent, the inverse tan of this angle. So that angle is 43 degrees. Okay, but the question's not asking us for the momentum of the second ball, it's asking us for the velocity of the second ball. But if we know the momentum of the second ball, we just need to divide it by its mass to figure out the velocity of the second ball. So our final step over here is to take the momentum of ball B, the total momentum of ball B, and divide it by ball B's mass. So the velocity of ball B at the end, VB2, is equal to 0.513 kilogram meters per second divided by its mass, which is 0.3 kilograms. So we get velocity of ball B at the end, it's a vector, is equal to 1.7 meters per second north, 43 degrees east. So this is just another strategy you can use. Because the conservation of momentum really is just what momentum is there at the beginning, that equals the momentum at the end. You would have to account for what's all the momentum at the beginning, and it should match the momentum at the end. So in this case, I didn't make full equations using the conservation of momentum. Instead, I just figured out each individual momentum, and then I could put it all together in the end in this step over here. Okay, and that works totally fine as well.